and start with taking derivatives again using those formulas or so-called power rules for finding derivatives. So if I have the nth power or any power to differentiate, then I need to simply subtract 1 from the power of x and also put the same power as a factor in front of that power of x. So to recall how we did this, I can look at exercise number 5 and find derivative of function with equation 4 times x squared plus 3x and also minus 1. So to find its derivative, I'm going to utilize this formula above and take number 2 multiplied by 4 and produce 8. And the power of x will be 1 because 2 minus 1 is just 1. So when people have first power, they usually don't write it. That's just x on its own, right? Now we also had a property of derivatives such as a derivative of x, and that was equal to number 1. So for the next term, its derivative will just be number 3, right? Because derivative of x is 1, so I don't need any x's with this 3, so just 3 multiplied by 1, and that's it. And finally, the derivative of -1 is 0, so it just disappears. So we find derivative of this, and the way they write it sometimes is dy over dx. And that means the same exact thing as a y prime. So sometimes they write derivative with a prime, sometimes with this dy over dx. In fact, in the section 1.8, they also discuss second derivative, and they write it as a d2y divided by dx squared. That looks kind of unintuitive. That's why I never want to write it like that. I prefer y double prime. So if you take another derivative of the y prime, then all you get is just number 8. And that's what exercise number 5 is asking us about. Find the second derivative. So there we go. We found that second derivative. And we also can find a third derivative. We can use the same pattern, and I can differentiate this again. Why not? If I take another derivative, so I can write it as a 3 primes, and it's going to be 0. So third derivative is 0. I can also find the fourth derivative and the fifth derivative, and etc. But it turns out that there's no point because already all of them will be zeros. So you can keep on differentiating again and again, and sometimes it is useful, but we don't go any farther than the second derivative. And in the next chapter, we'll see why. What is the use of that second derivative? So I'd like to do one more exercise, like problem number 11, that should refresh a little formula that we also used before. The formula says that derivative of a square root is a fraction 1 divided by 2 of these square roots. So if they want me to take a function square root of x, then I already know how to find its first derivative, because again, they want me to find the second derivative. And that's why I'd rather prepare this as a x raised to the power of -1/2, right? Because that square root that formula gave us is actually power of 1/2, right? And then I can bring this 1/2 up to numerator and change its sign to -1/2. So I'm prepared to take another derivative. So we can do this again. So I put 1/2 the way it is, and then multiply it by -1/2, right? And then we have to subtract number 1, as we always do, from that power. So let's see how we're going to do this. -1/2, and I need to minus another 1, just like that. Excuse me. So it looks like then we're going to have a -1.5 as a power. So I could just add 1.5 and get 1.5 or 1.5. So to write the answer a little nicer, I can keep the minus on the outside. 1 is going to be my numerator, right? 2 and 2 multiply on the bottom will be 4, and x I'll bring down, raised to the positive power of 1.5. Some people may like to write it with fractions. It is up to you. It's the same thing. So you can put positive power, and that's good enough. So you can find another derivative and then another derivative of this, but again, they just want a second derivative here, and that's good enough. So the point of this last section is that you can take derivative and differentiate it again. And again, if needed. And that concludes chapter 1. Finally, we're going to get to look at chapter 2. And that chapter is actually working with derivatives again, but it gives us intuition why we actually need these derivatives as applications. So where we can actually utilize those derivatives. And the application that we have here is talking about finding the maximum points as well as minimum points on the graph of your functions. So when you know that we have here so-called local maximum and down below local minimum, then what we can do is just connect them with the curve and get a pretty good idea how the graph is going to look like. And that's the key part of graphing. And turns out that derivatives is all we need for this, because if I find derivative and set it equal to 0, I will be able to get the fact that at those points, slopes of lines tangent to the graph will be equal to 0. And that's exactly derivatives. So we find derivatives and we set them equal to 0. That's really all we do in the chapter 2. So let us do the exercise just to see how we can actually do this in practice. So let me find where the section end is. So looks like the exercise set is here, 2.1. So let me try problem number 1 to start. Exercise number 1 says find derivative of the function. So what I'm going to do is I'm going to find derivative, and I'm also going to use it to graph this parabola, isn't it? It has x squared in it, So we can actually take derivative, and this will be a f prime. And what is this? It's going to be 2x, right? For the x squared, 2x to the first power, plus, and then derivative of x is 1, so it's just plus number 4. So I need to set this equal to 0. So that's the key part of solving this exercise. And then I will be able to find what value of x actually makes this derivative equal to 0. And looks like it's -2, isn't it? X is equal to -2. So here we have the value of x, and we found that special so-called extremum point, they call it, 0 of first derivative. And now I can graph this parabola. I just need to graph equation that they gave us, and the key point that we just found is that vertex of parabola. So let me calculate its coordinate. So when x is equal to -2, I just plug -2 instead of x. There are 2 spots where I see that negative number 2. So we get a -2 squared, and then plus 4, which is multiplied by -2. And also there is a 5 added to the end. So it's 4 minus 8 and plus 5. And this is number 1. So when x is equal to -2, f of x, remember we call it as y, is equal to number 1. So let me plot this point and get the graph. -2 for x and plus 1 for y is someplace here. And then here we have some parabola that goes up. Please notice that this vertex, this lowest point on a graph, is the most important, because once I plot that point, that's it. I produce the graph of parabola. And all I care about is derivative to find that special point. If you remember from previous class, the college algebra, they used to complete square, they used to go through some unpleasant procedure to find the vertex, but we just take derivative and we see when it is equal to 0, and for that lowest point on the parabola, the tangent line has a 0 slope. In other words, it is horizontal tangent line. So one can say, Alex, I already know how to graph parabolas. Let us graph something other than parabola. Maybe exercise number 7 be interesting, because that's the cubic function, right? It's a friend of a function with equation y is equal to x cubed, because the largest power that I see here in exercise 7 is x to the power of 3. So let me find derivatives for this function, capital G of x. So we have x to the 3rd power minus x to the 2nd power. And then we subtract x and subtract, actually add number 2. So let me do the process. Derivative of function g. 3 is what I put on the ground and multiplied by x squared, right? Then next term will give us minus 2 times x, and finally -1. This is my derivative. I can also find the second derivative. Why not? The second derivative, we just did it in the previous exercise, is what? 3 times 2, right? I differentiate what I just produced. So it's a 6x and then minus 2, and I got another derivative. I say, Alex, I want to find the third derivative. Well, we don't need it for this exercise. It turns out that to graph, it's enough to have just first and the second derivatives. So now I can find x, and I will try to factor my first equation. So 3x squared factors as x times x, and -1 factors as 1 times -1. It's not much of a choice we have here. So from the first piece, from the first factor, I set it equal to 0 and find x, as well as I find x from my second factor. So the second gives me just number 1, right? X is equal to 1. And the first will tell us that 3x is -1. So x is equal to -1/3 minus 1/3. Okay, this is great. So we produced 2 special numbers. And then I will get another special number. I'm gonna make my second derivative equal to 0, because again, the only reason why we find those derivatives is just to make them equal to 0. So when I divide both sides of this equation by 6, I get 2/3, which is 1/3. I say, does it have anything to do with -1/3 that we just produced? Not really, but I need to plot those points on the plane of coordinates. So I'm gonna just try to calculate y coordinates, just like I did in the previous example. So I need to find 3 values of function, and I guess I better use calculator for this, because in the function g of x, in the one that they gave me, originally I need to put number 1, so I need to find g of 1, then I need to find g of -1/3, and finally g of +1/3. I need 3 values so I can plot those 3 special points, and then we will see what this is all for. So the first one, when I replace x with +1, I'm gonna probably be able to calculate this without a calculator, right? Because 1 cube is just 1, so I can cancel these 2, and then 2 minus 1 will be just 1. And of course, again, it's probably a good idea to just put this in a calculator and double check. Especially, I would say it's a good idea to put in a calculator values at those fractional numbers, right? So I'm just gonna write this, and then I will plug them in the calculator. So it looks like I have to be careful. This is a minus here. I subtract the next term. And then we also subtract the last one, again 1/3, and then add 2. And I don't want to start messing with all of these fractions. Let's just put them in the calculator, because technically it's formality. What type of a fraction you have, you just approximately can use the decimal value to get the result. So let me show you how I would recommend to do this. I just need to find the favorite scientific calculator. And I usually use that Desmos. It's totally free. So we can put parentheses to calculate that minus 1/3 raised to the power cube, right? Minus. So notice that I just plug it in the way it is. I don't try to do any intermediate calculations to help a calculator. Believe me, calculator is not going to appreciate it because it doesn't care. So I just put the numbers where they are, like that. Just don't forget about square for the -1/3. So I put power of 2, like that. And then plus 2. So there we have 2 and a little something. So if you produce 2 and some 9s or 27s, wouldn't make sense, make difference, I guess. It's a little bit more than 2, and that's what we really care about. When you say, Alex, that was tedious. Yes, but it will help us now to calculate the last one. Notice the last one does not have a -1/3, but +1/3. So what I'm going to do is I just take away these minuses inside the parentheses, replace them with nothing. So this way we get a +1/3. And here I have the answer. It's 1 and something. 1.59, ... So the idea is that now when you plot these 3 points on the plane of coordinates, you will get yourself a very nice graph. Just look at this. When we have 1 for x, there is 1 for y. So here's my first point. That's the one that corresponds to x equal to 1 and y equal to 1, because that's x, and that's a g of x, which is y. For the next point, -1/3 is someplace here to the left from 0. I've got the answer, which is a 2.185, so something a little bit up higher than that. Right? 2 and a little something. That's just approximate 2.185. And then we also calculate value at +1/3, right? And at +1/3, I produced another value, 159, which is somewhere in between of 1 and 2 and something. So now question is, what should I do with these points? And the answer is make a graph such a way that one end will go up and the other end will go down. Analog of cubic parabola. So we already see that there is going to be a minimum value and another will be a maximum. So what's the role of the next point? And the answer is this point when we're going to change the way the function looks like. So instead of function kind of resemble the parabola that opens down, now it will resemble the parabola that opens up. And that's why we call this point a so-called inflection point. The function inflects there. So that's a second derivative, 0 of it. That's where we had 1/3, right? And that's exactly the one that corresponds to this change of behavior of that function. So that's the idea of second derivative. When you find it and set it equal to 0, you see the inflection points. And for the first derivative, zeros of that first derivative will be a minimum and maximum. And that's pretty much entire theory that appears behind those derivatives. And what we can do is just try another little exercise, maybe for a change. I will try one with force power. How about that? We didn't have many chances to graph force power functions, right? So now we're going to have a good chance to do this. And I will follow exactly the same set of steps. So I'm going to find the first derivative, and then I'm going to find the second derivative, and I'm going to make them both equal to 0. And that's really all that brings us to those special points, the maximums, minimums, and inflection. So let me try 21. So we have a function g of x. Now the largest power is 4. How about that? 2x to the power of 4 here. And also minus 20 multiplied by x to the power of 2. And then plus 18. So this is a fourth degree function. And it's similar in shape to the parabola x squared, but that's x to the power of 4. Turns out that all even functions have similar shapes. So let's follow the process. So the first step is to take a derivative. So 4 is on the ground and x is raised to the power of 3. Next, I multiply 20 by 2 and get 40, right? And it's times x, because x squared, so it's first one. 18 disappears, and that's great. So now I'm gonna find the second derivative, and then I will set them both equal to 0. So second is gonna be 12, right? 4 times 3, 12x squared, and then minus 40. So we got first derivative, we got second derivative. That feels good. So now we need to solve a couple of equations. We make them both equal to 0. So to solve the first equation, I factor out 4x, right? 4 times x. Okay, so next factor will be x squared minus 10. Okay, so when I write this equal to 0, then the first factor just tells me that x is 0, right? They say it's a first derivative 2 times 8. Oh, thank you. Thank you for telling me. Thank you for telling me at this stage. I almost finished with this, but now I'm going to need to change it a little bit. And that's great that you noticed. Thanks again, because notice that 8 is what I have to factor out, right? Because it's 8. So that'll be 8. It's not going to change much my first answer, but looks like the other answer, it'll change, because when I factor 8 from 40, it's going to be not a 10, but 5. That's going to be a little bit different. So it's good that you are doing this simultaneously with us, because otherwise it'd be a little bit different, right? 8 times 5 is 40. Okay, so see, it's been too long of a break, right? I over-relaxed. So now I need to concentrate a little bit better. So the other piece will be 24, right? Here, okay. 24, let me clean this mess, write it a little bit nicer. 24x squared. Okay, now it's the way to go. Yeah, please check if I make a mistake, because if so, just let me know, please. So 8 is what I can take out, right? Or actually, this one I can solve right away. This be 24x squared is equal to 40, and then we can find x, right? And from that other piece, it's x squared minus 5 is equal to 0, right? And from there, we also find a couple of solutions. So x squared is 5. And when I do this square root extraction, then I get the square root of 5, right? And there are actually two of them, plus and a minus. See, it gets very tedious. With this higher powers, you can get all kinds of answers. So was the case with my last equation, it looks like I need to divide both sides by 24, right here and there, and this cancels a little bit. So what is that I get? Let me give a little bit of a room. So looks like it's 40 over 24. I can reduce them by 8, right? So x squared will be 5/3, looks like. Okay, so x is equal to plus minus square root of 5/3. Can you imagine there are 5 numbers that I need to work with? Well, what makes me feel better is the fact that this is going to be even function. Just like here, x to the 4th, even power. And that is why I can just graph whatever is to the right from my y-axis, and the left side will be a mirror image. So the point is, I don't need to worry about negatives here and there, because when I raise them to the powers of 4 and 2, they give me the same thing as if they were positives. So at least that will make our work a little bit easier. But other than that, we ended up with not very pleasant looking numbers. But the good news is that we have a calculator, and the calculator is ready to help you. And the good news, it's also a free calculator, so you can use it as much as you like. So let me get function g calculated at 0. Now I just noticed that whether I use positive or negative, it doesn't matter. So the result will be the same. So I can say at plus minus square root 5. And finally, at the last one, which is a fraction, square root 5 over 3. And definitely I want to use calculator for this. So what happens at 0? Well, looks like pretty much everything will disappear, just the last term, right? So this one I can do by hand. So 20 times 0 squared, and then plus 18 will give us just 18. And that feels great. The next one, I need to plug into this function square root of 5. I'm not going to put plus minus. I just try to show you that the result is going to be the same, no matter if we have it positive or negative. So I go with 2 square root 5 to the 4th. If it be negative square root 5 to the 4th, it'd still be the same result because it's a 4th power. It'd still be positive. Next is again square root 5, but now it's squared. And finally 18. And similarly with the third piece, right? So it's this fraction, square root 5 over 3, power of 4. And the next is power of 2. It is a little bit tedious to write, but I think it's a good idea because, first of all, it teaches patience, if you like, but it's always great to prepare. Remember, on the exam, I asked you to show work. Of course, I'm not going to ask you for something nasty like that because it's really a little bit too much, but it's still fun. So let me go for the calculator. And looks like the first one is just 18 because first two pieces are both 0, so they just disappeared. So what's the next one? Now we have to put a square root 5 here in the parentheses, right? And then raise it to the power of, oh, yes, I should be careful. Pay attention where I put parentheses. Okay. So raise it to the power of 4. Then minus 20. And again, I put parentheses because I want to square this thing. So radical 5 and then squared. When I say, Alex, is just the 5. Yeah, but again, I don't want to help this calculator. I just put in everything the way it is and get myself the answer. So it's minus 32. Okay. Now for the last one, notice that I can edit this square root 5. What I'm going to do is divide this by 3 like that. And same with the next square root, 5 over 3. So you can get the answer. Because once you already started to enter numbers in the calculator, then it just goes and you get yourself a nice answer. 9.77, whatever, . So we've got some points to plot in here. And the first point is at 0, we have 18. So that's the one I put somewhere on y-axis, right? 0 and 18. So that's the first one. Now there'll be 2 points with radical 5. That's a little bit more than 2. So one of them is on the right side and the other is on the left side. And when we have the square root of 5 plugged into the function, then negative 32 comes out. So that'd be all the way down on the level of minus 32. Okay. That's look good. That looks good. So we got 2 points here and here. Symmetric, because again, it's even function. And then I will get the last ones. Square root 5 over 3. So they'd be a little bit smaller, someplace closer to 0. So it's radical 5 over 3, as well as its mirror image on the other side, negative radical 5 over 3. I have values of function that are going to be negative 9, something like that, negative 9 point something, 7 or 10 almost. So I got 2 more symmetric points. So one is here and the other is on the other side. So now comes into play this picture of parabola-like function that both ends going upwards. One goes up here, the other goes up there. And then I need to continue in such a way as if it was a parabola-like. So people say it's concave up. It's just like parabola that opens upwards. And then starting at those points, we use parabola that opens down. So we produced a pair of points of inflection. And you can see that the graph is pretty clearly produced in here, right? I didn't need any graphing calculators. In fact, if you try to use one, then definitely you won't be able to clearly see those minimums and the maximum points, as well as points of inflection that we calculated using algebra. And this is definitely the way to graph. And it shows us how powerful the calculus methods are. So I guess that's very impressive, right? So those lowest and highest points of graph is what we really care about. So how about if you try to find the, looks like, lowest point on a graph of parabola and exercise number 2 for a little quiz for today. So all you have to do is the same thing that we just did in all the exercises, find derivative and set it equal to 0, right? And tell me what value of x it is. So find coordinates of maximum point on this graph. And again, maximum point, minimum point on this graph, because it opens upwards. Should be careful. Minimum point, the vertex, in other words. And this is going to be, again, 0 of our first derivative. For a parabola, we don't need second derivative, right? So you just need to tell me what would be 0 of first derivative. And that's pretty much all we need for today's little quiz. And I guess after that, you can relax a little bit till Thursday. And to finish up with your homework, I'm still waiting. I give you extension on this. I still give you a full credit, but make sure that you send it to me. Otherwise, I can't give you any credit because I don't see it, right? So make sure that you send me your homework. And I think that pretty much all the class sent it to me. Yeah, just 2 people. Yeah, oh, everyone sent it to me, just one person. So anyways, find the vertex of this parabola. So make it equal to 0, that first derivative. And then you can relax.